Hello and welcome. RISC-V Instruction Set. Introduction. In this video, I'm going to look into the RISC-V Instruction Set. Now, this is a very brief introduction to the RISC-V Instruction Set, and it is not intended as a comprehensive study of the RISC-V Instruction Set. Instruction set. Before I go any further, I'd like to draw your attention to this document here. Now, this is the RISC-V Instruction Set Manual, Volume 1, UserLevel ISA, version 2.1. Now, you can download this RISC-V Instruction Set from the RISC-V website. I have provided the link in the description. Okay, so the RISC-V Instruction Set Manual, Volume 1, defines the base ISA. ISA stands for Instruction Set Architecture. Example, RV32I and RV64I. I'll come back to this later on. And basically, it includes integer instructions, formats, and register usage. Secondly, it specifies optional standard extension. For example, M for integer multiplication / division, A for automate instruction, and etc. Then it also describes the programming model, which includes register naming conventions, calling convention, reference, and instruction behavior visible to software. It also standardizes how software interacts with the RISC-V CPUs. Basically, that ensures that compilers, assemblers, operating systems, and toolchains can target RISC-V in a consistent and portable way. Definition of instruction set. Now, before I go any further, let me define what is an instruction set. An instruction set is also known as instruction set architecture, as mentioned earlier. It is a complete collection of machine-level instructions that a particular CPU or processor that is designed to understand and execute. Now, currently, there are two main traditional classifications used to describe CPU instruction set design philosophies. But it is important to know today CPU often blend both approaches. And these approaches are the CISC, CISC, Complex Instruction Set Computer, and the other one is RISC, RISC, Reduced Instruction Set Computer. Now, before I go any further, I'd like to talk about Complex Instruction Set Computer, CISC, CISC. Let's take a look at CISC. CISC is a contrasting CPU design philosophy to the RISC and RISC-V processes. A single CISC instruction can perform multiple low-level operations, such as memory access, arithmetic computation, and control flow within one instruction. Now, the instruction set is generally large and complex, containing instructions that may take up multiple cycles to execute. A common example of a CISC architecture is the x86 family of processors, used in both desktop and laptop computers. Now, due to the complexity, CIS instructions often require more complex decoding hardware, which can affect performance and power efficiency. Now, however, the boundary is not as strict anymore as it was originally. Processor like the Intel, AMD, even ARM uses a hybrid model. For example, the x86 CIS processors internally decode complex instructions into simpler RISC-like micro operations. Likewise, the ARM, which is a RISC-based processor, have added some complex instructions for performance and power efficiency. RISC-V Instruction Set, Base Instruction Set, and Standard Extensions. The RISC-V Instruction Set consists of a base instruction set and a standard extension. Now, the base instruction set, that is the RV32I and RV64I, or RV128I, these are collectively known as the integer base instruction set, and it forms the core set of instructions that every RISC-V processor is required to support. Now, the terms RV32I, RV64I, and RV128I refer to the base RISC-V instruction set configurations, and they define both the word size of the processor and the base instruction set. Hey, so what does RV32I, RV64I, and RV128I means? So the RV is short for RISC-V, and the 32/64/128, that is the word size, the number of bits in general purpose registers and pointers. And the I here means the integer base instruction set. Base instruction set. Now, the base instruction set includes the following: the integer arithmetic instructions, that includes add, subtract, well, here I think it's multiplication, ADDI, that's add immediate, and so on. Next comes the shift instructions, and then followed by load/store instructions. Now, I'm not going to go through these instructions here now, but I'm just pointing it out to you. Next is the control flow instructions. By that, I mean instructions like BEQ, branch when equals, BNE, branch not equal, and so on. And then followed by the environment instructions. These are things like eCall, eBreak. eCall is for environment call, used for system calls. Let's take a look at a couple of RISC-V base instruction. Here we have an add instruction, that is the RV32I, is the R-type instruction, and it's the integer addition. Then you have ADDI, this is a RV32I, I-type instructions, integer addition with immediate. Standard extensions. Now, additional functionality can be added by including optional standard extensions like M, which we have encountered earlier, that is used for integer multiplication and division. Then we have F for single precision floating point, D for double precision floating point, A for atomic instructions. Again, we have mentioned this earlier. C for compressed instructions, V for vector processing, B for bit manipulation, and then finally the J here is for dynamically translated languages. Now let's take a look at these two instructions here. We've covered this earlier. The MUL is the multiplication instruction. It's not part of the base RV32I instruction set. It comes from the M extension, which stands for integer multiplication and division extension. And you please take note that M extension also support integer division. Now the same notation here applies to fadd.S. This is an F extension. It's the R type instruction, and it's for floating point addition. Now FADD stands for floating point add. The S here is for single precision. All right, this conforms to the IEEE 754. Now, RISC-V uses several instruction formats, and I have summarized them here. You have heard me mention the R-type instruction, the I-type, then we also have S-type, B-type, U-type, J-type. Now the R is for register arithmetic, I is for immediate and loads, S is I-type, S-type instructions is to store to memory, B branches, U for upper immediate, and jumps, for J for jumps. And here are some of the example. For R, we have add X, X2, X3. For immediate, we have ADDI, LW, E call, and so on. So this is for store, SW, the branch here, and the upper immediate, U type, the instruction, and the J type for jumps. All right, here's an example. Pseudo instructions. Now here is a table of the most common pseudo instructions used. Now please be aware that there are more operations, more pseudo operations that are not shown here. All right, so please be aware, also be aware that not all RISC-V assembly language programs are written using pseudo instructions. Now, pseudo instructions are often used for readability, convenience, and simplicity, especially in teaching handwritten assembly and debugging. Now, before I leave this table, let me just point out to you this instruction here, the hex code here. This triple I here, that is a 12-bit signed immediate number. All right. M and N are placeholder. N is the source register, RS. M is the destination register, RD. So M and M are registers number. Now, I mentioned different types of it's a RISC-V instruction format earlier. So what I'm doing here is I'm highlighting the I-type format. This is a 32-bit instruction type. Okay, so we have the 12 bits here. That is the immediate. All right, RS 1, 5 bits allocated. That is register source 1. And then here, this function 3, that's 3 bits. Okay. RD, register destination. All right. And then finally, opcode, 7 bits allocated. That is the operation code. So this is the I-type format instruction. Now, consider the following text segment taken out from the RISC simulator. Now, for those of you not familiar with the RISC simulator, I have used the RISC simulator in my last video. So if you're not familiar with that, please refer to that video. So here I have, this text segment here, I've taken it from the RISC simulator. Here I've highlighted the LI A0, 5. This is the pseudo instruction. All right. And then the real instruction, which is this one here, that is the ADDI X10 X05. All right. So this is the real instruction, and the hex code is shown here, which is 0x, that represents hexa 005000513. Okay, this is in hexa. Right, let's convert ADDI X10 X05 into binary. So as we said earlier from the take it up from the table, ADDI X0 so X10 X05, the hex code is this. Now if you convert that to binary, that would be this. Now this is color coded for a reason. Just give me a moment. So for the I-type instruction, just a quick reminder, these are the this is the format. All right, the immediate RS func3 RD opcode. Now if we then move this what we call hex code down here, and then split the digits according to the format. So this represents the IMM. The blue one here represents the RS1. These 3 bits here is the func3. RD, which is 5 bits, is represented by these green bits here. And then finally the opcode. All right, so that is the I-type instruction. Okay, that's it for this video. I hope it has been useful. Thank you for watching, and I'll see you in the next video. Bye!